Okay, welcome back. I hope we enjoyed the snow day. Because of the snow day, we've got a new calendar, so make sure you grab one from the tables. It's projected here. Everything has been pushed down another day, so all the tests and quizzes and projects are now due a day later than they were before. So today, we talk about two new integration techniques called partial fractions and trig substitutions. Just putting it out there in the beginning. Today is going to be a moment where we reflect and think, wow, look at the great lengths that people used to go to find antiderivatives before they had technology. Just putting it out there. These are challenging techniques, and these were the only things that people had before the technology.
So you're going to show us this on a smartboard?
Yes. All right, other thing I'm going to say is that next class, that is this coming Monday, I'm going to ask you to choose how you want me to grade you. So just to remind you, on the syllabus, there were some different options for how I calculate your grade at the end of the semester. If you've lost the syllabus, it's up on Moodle, so you can have another look. So if you go down, you'll eventually find all these different grading options: standard, test heavy, test light, or you can personalize one at the bottom. Jeremy, you can move somewhere else that there are people sitting at. Or you can stay at the donut table, that's fine. So I'm going to ask you to choose on Monday. Now, on the test, I said if the course ended today, your grade would be blah. That was assuming the standard grading choice, unless I wrote something otherwise. So that could change when you make your decision on Monday. Any questions about the decision you're making on Monday? Okay. So other things coming up, we've got a project that I will hand out on Wednesday, and then it'll be due a while after that. Our next quiz is coming up 1 week from today, Friday, March 8th, okay? All right, so let's come back to here. And if you open to page 1, you'll see a reference sheet that you're going to bring with you on the quiz and on the test. It has to do with the stuff we are looking at today. But let's go ahead and jump ahead to page 3. And we will start. Who's on page 3? Alex, can you read number 1?
Today we cover two integration techniques that very few people like: partial fractions.
Resorted. Okay, so let's take a look at this first integral. Integral of 5x minus 10 over x squared minus 3x minus 4. Let me put out there, the first technique you think for any integral is going to be basic u substitution. That's always the first thing to try. So if you try letting u equal the denominator, right? Oftentimes if you have a complicated denominator, you try that. Don't write this down. What's du? 2x minus 3. Can you make the numerator out of 2x minus 3? No, it just doesn't look, it doesn't look like 2x minus 3. All you're allowed to do is multiply or divide. So like you can multiply by 5/2 or something, but it won't look exactly like the numerator looks. So this is not going to work. So here's the new technique. New technique involves this. So you can write this part down. So I'm going to rewrite the integrand, just the fraction. And well, we had problems like this when we were doing the table of integrals day. What was our technique when we saw this kind of, is to factor the bottom. So let's factor the bottom. Plus 1 minus 4. Okay, and then as soon as it looked like that, then we had our integral table. So I've got it up here. It's number 27, right? Cx plus d over x minus times x minus. And it involved two different ln's. We had no idea why this formula was true. So we're going to now figure out, we're going to get this answer, but without relying on this table. What's that? Yeah. Okay, so here's the idea. Don't write this down. Suppose that I gave you something like this: 3 over x plus 1 plus 7 over x minus 4. Don't write this. And I asked you to add them together. What would you first have to build? A least common denominator. What would the least common denominator be? Multiply. So then over here, we'd stick what? X minus 4, and therefore Also upstairs, you'd have to stick x minus 4. And then downstairs, what would we need? X plus 1, so upstairs, x plus 1. And then if I asked you to mush them together, you would distribute, you'd have some x's, you'd have a constant, you'd have some x's, you'd have a constant, you'd add them together, and you'd get some x's and a constant. Yes? So perhaps you might get 5 x's and a constant of minus 10. It's possible, yes? I don't think so either. I just made the numbers up. But do you buy that perhaps for different numbers, I put 3 and 7 up here, but maybe for some numbers, we could actually get exactly 5x minus 10. It's possible, right? Okay, now why might that help us? Well, let's go back to the numbers that I made up here. Oh, going the wrong way. So if we had this, again, don't write this, and you had to integrate, could you integrate 3 over x plus 1? How? Do substitution. We let u equal x plus 1. Derivative would be 1 dx. So the integral we would have would be 3 upstairs, downstairs would be u, and then there'd be a du. Okay, the 3 you're still not writing this. I can put the 3 out there. 1 over u du. It's on the take-home quiz. That's ln of u. Yes? So if somehow we can figure out, it's not 3 and 7, but if we could somehow figure out what it is, we can handle them. We'll get 2 different ln's, which actually kind of makes sense. If you remember on the formula here in 27, there's an ln, another ln. That's why. It's because they're doing this technique. So let's try it. So the hope is that we're going to be able to find some numbers to put on top of each denominator. You can write this part. But instead of putting 3 and 7, which I just made up, and there's no way those are the right numbers, we're going to put numbers to be determined, A and B. Iris. Okay. Any questions on why or the motivation? Like this is going to work, right? We understand the basic idea. If we can find A and B to make it equal 5x minus 10, it's going to work. So I'm going to put a line over here. I'm not looking at that. I'm just looking at the second part of this equation. If it's a minus, then B will just be a negative number. So I'm always going to call it a plus. Good question. Okay, the idea here is to multiply both sides by the LCD. So we're going to multiply both sides by what? So on the left-hand side, when I multiply by this thing in red, lots of stuff cancels. What do we have left? That's just the left-hand side first. When I multiply this thing right here by this thing, we just get the 5x minus 10, right? Okay, so 5x minus 10 equals, all right, and then Topher, I think this is what you had said before. When we multiply the first fraction here, the a over x plus 1, by this red LCD, the x plus 1's cancel, and you still have the x minus 4. Plus, there's another term. If you understand where the first one came from, you should be able to figure out the second one. What's that? Oh, you're way ahead of us. Way ahead. Yes. Yeah. Any questions on where those pieces came from? So far, so good? All right. Again, the goal was to find A and B to make that first equation true. The bottom equation in blue is true for every value of x. It's supposed to be true all the time. We're going to pick some particular values of x to make good things happen. For example, Topher, if we pick x equals 4, what nice thing happens? The a part goes to 0. So we're just going to pick x equals 4 because that makes our life easier. Let x equal 4, and then we're going to solve for b. So all of the x's become 4s. And then we can find b. Oh, right.
Well done.
All right. So we're going to solve this equation right here for b. So let's find b. What do we get on the left-hand side? 5 times 4 minus 10. 10 equals no a's plus 5 b's. So b is 2. Everybody okay with that? So if you understood why x equals 4 was a good number, then you should be able to find the other value of x that's a good number. Plug it into that same blue equation and solve for a. Go ahead and do that and check with your neighbors. I got a equals 3. Any questions on finding a or b? Okay, so now we're taking the a and the b that we found, and we're just going to go back up and rewrite the original. So we'll do this here in purple. So this integral, I'll put right over here, I'll call it I for original integral. Turns out is equal to a over x plus 1. What was a? 3. 3 over x plus 1. Plus d over x minus 4. 2 over x minus 4. Everybody see where that came from? Mm-hmm. Any questions on the purple? Gotcha. Okay, Jeremy, you all right? All right, so now we've got two little integrals over here. We're going to do, what are we going to do? We're just going to write the answer. These are u substitutions, but they're very simple u substitutions. That 3 can come out of the first integral, ln of what? X plus 1. That's the first part. It's a little u substitution. We're not writing out the details. I'll write them later on if you want to see them. Plus, and then the second integral. Good. Questions on that? It's done. Yeah, let's just look real quick at the thing in the book. So formula 27 has a cx plus d, x minus a, x minus b. Can you write down, you'll have to look at it on your paper, write down the values of a, b, c, and d. Write down all 4 of those on the paper. A, B, C, and D. How much is A? B? Wait. Yeah, I want little a. So let me write the original. What was the integral? It was 5x minus 10 over, what did we write? X. Okay. Yeah, so that's what we have here. So a is equal to -1. Everybody see it? Because the formula here has x minus some number. X minus -1. How much is b? It's 4. C is next to x. It's 5. D is next, is the constant term. Close? Negative 10. Got to capture that negative. A and B could be swapped, yeah. Okay, so let's just look at a little bit of this and see if it agrees with what we had gotten. So 1 over A minus B, how much is that? 1 over negative 1 minus 4. Negative 1/5, is that right? And that's not in our answer anywhere, so presumably that's going to cancel later on. Let's take a look at this piece, AC plus D. Figure out what that's equal to, AC plus D. Negative 15. So that's going to get multiplied by negative 15 ln of something. What do you get when you multiply those? 3, the 3 that we got in the front. So it does agree. Of course it agrees. It's got to work. But it's kind of nice to now have a sense of where did this crazy formula come from with 2 ln's? Well, it came from this new technique called partial fractions. All right, let's come back here and take a look at this next one. X squared over x minus 3, x minus 1, x plus 2. This is not in the table. The ones in the table only had 2 terms. So let's see if we can figure out how to set this up. X squared over x minus 3, x minus 1, x plus 2 equals. So we're going to write it as the sum of some fractions. First denominator, x minus 3, upstairs, some number A to be determined, plus downstairs, and then, good. Everybody see the setup? Is there reason to believe we might get an x squared out of the right-hand side? Because upstairs, when we did this first example, there was no way we were going to get an x squared, right? When we did, I had numbers up here, I think 3 and 7. And so we had like 3 of those and 7 of those, and there was no x squared anywhere, right? It was just a number times x and a number times a number. No x squareds coming out there. So is there any reason to think there might be x squareds coming from down here? That's right. If we're gonna add these fractions up, the LCD is all of this, which means what is this guy missing? Right. Right. That's what it's missing upstairs and downstairs. So yes, you will get some x squareds. All right. So let's see if we can do the algebra part of this. So we're going to multiply both sides, every term, by this LCD that's underlined in purple. What will we get on the left-hand side? Just x squared equals a times. So again, we're multiplying each fraction by this LCD in purple. What will cancel when I multiply this guy by the LCD is the x minus 3's. What will still be there upstairs? That's right. And in the next fraction, what do we have? Okay, somebody, not Joey, not Topher, last term. Good. Everybody see where those pieces came from? Iris? That's the ultimate result, yeah. Really what we're doing, and I just didn't write it out because I didn't have the space, but we're multiplying both sides of this equation by all 3 denominators. And then when I bring this thing in, it's going to distribute to all 3 fractions, yes? And let's just look at what happens when it distributes into this fraction right here. Right. So that's why the result is what you observed. So, but it's not, we're not intentionally writing the other two denominators, that's just the outcome. Okay, so with your neighbors, find a value of x that will make good things happen here, solve for either a, b, or c, repeat 2 more times, and then do 3 integrals when you're done. We'll spend a few minutes on this, so work with each other, see if we can get the final answer. Okay, we've got our 3 values of a, b, and c, and then we've got the integrals, 3 separate ones. Any questions? We forgot the stamp. Thank you. Let's see. Any questions on this?
That's a CQ.
All right, I'm going to make a slight tweak to this problem. Suppose that this had been a 2x minus 3. It feels like all we need to do is that, yes? Vince, what's the problem? In the denominator that'll be pulled out. Okay, so Nikki is saying that maybe that would be a 9/20. And I actually think that is the right final answer. How'd you get it? Cheers. Vince, you saw the 2 down there as well?
Yeah, so we're going to have to change factor when we solve whatever.
The algebra will change. I think there's a calculus thing that's going to change here. 9/20 is the right thing down there, but I think it's there for a calculus reason. We didn't write the steps, but how do we get ln? Where did it come from? It's a 1 over u, yes? So in our minds, it was such an easy u substitution, we didn't write it. But what would you let u equal in this case? 2x minus 3. Now what is du? Is 2 dx. You see the over 2 that's going to come in here, because that you have to solve for dx, and you'll have a du over 2. So I'm just putting it out there. It's not always a clean just ln of the thing. There is an actual u substitution that happens there.
Can we just go over why you have?
I just put it in there so that to highlight that it's not always a simple just stick an ln and that's it. Because this answer actually would have been exactly what Nikki had predicted. It would be you'd have to take that 9/10 and divide it by the 2 that pops out of the du. So it would be a 9/20. So maybe this is, well, so it's not a double fraction yet. I mean, it's a 9/10 over 2x minus 3. If you wanted to factor the 2 out of this thing, you could. I didn't, that's not what I thought you were saying. That's not what you were saying, was it?
I was just saying, I think that I might for the get rid of that 9/10 over this thing by multiplying 9/10 by 1 and ending up with a simpler.
Yeah. I think there are other algebraic alternatives here. So maybe I'm just not understanding where because you got the right thing. You said 9/20, and that's absolutely right. So maybe right after class you can show me exactly, because I don't quite follow where like I see 10 and 2 makes the 20, but I'm missing something. So maybe you can show me right after class. Okay. So on the next page, there's a process written out for how do you do partial fractions generally. It turns out that things can get a little bit messier than we've seen. So we're just going to jump to number 5, and you can read through the explanation later on. But in number 5, we've got this crazy complicated denominator. we're not going to do the whole number 5 out. I just want to get the setup. That's the point of this example. So the first thing I see is x minus 2. What should I put in my partial fraction decomposition here? A over x minus 2. So that's easy, right? Plus. Then I have x plus 4 cubed. So to me, it feels like, okay, so then we have a b over x plus 4, and then a c over x plus 4, right? Because there's 3 of them, right? I mean, it's just shorthand, this exponent, but there's 3 of those guys out in the bottom. So you can write this. We're going to have to modify it slightly. Yeah, so let's write this, and we have to tweak it a little bit because it's not quite right at this moment. But that's how it seems from what we've seen, is that every linear thing down there just gets a letter on top. But the fact is, if you just add all these guys up, you get a constant over x plus 4, right? So it's really silly to have 3 of those things up there when essentially it's just a single constant on top. So what you need to do when you have repeated factors, like this x plus 4 cubed, it's repeated 3 times, what you need to do is raise these to ever increasing powers until you build up to the one that you have. This is a new thing. I'm not giving justification as to why you should build up, but just take my word for it at this moment. If you have repeated factors down there, you know, write them all up, building one at a time until you get to the actual power that's in the problem. So, that would be equivalent to what we had written before. No, because it could turn out. So if you just decide I'm not going to put that in there, it turns out it is not going to be possible to find A and B. So first of all, I mean, like, look at just this denominator. Are you going to get that denominator from adding these 2 fractions? No, if I just said add these 2 fractions, the denominator you get would be a single x minus 2 times a single x plus 4. You're not going to get x plus 4 cubed, right? So if anything, you're going to have that down there if you want any hope of the x minus 4 cubed over there. But it turns out that even this, if you were to add these 2 fractions up, it turns out there isn't going to be a choice of A and B that will get you that answer. You don't have enough freedom over here. You've only given yourselves 2 letters, A and B. Turns out that's not enough in a more complicated example like this. And I can show more details after class if people are interested in seeing them. But for right now, I'm happy just to say, hey, this is what the form is. Take my word for it. I'm not going to give you anything as complicated to do all the way out, but that's the form it takes. Plus, what goes next? Okay, we're going to have to tweak that one too, but it's okay to write it as it is at the moment. What's different about that denominator? It's an x squared, right? Well, if it was x squared to start with, like the very first example we did had an x squared in the bottom, what did we do? We factored, right? That was the very first thing that we did. So can you factor x squared plus 9 like we factored the first example? The answer is no. So if you can't factor the thing, then we call it irreducible. Here's the word right here. Irreducible, cannot be reduced into smaller parts. And if you cannot reduce it into smaller parts, it turns out that just putting a constant up there like e is not enough. We need to put something with x and then another constant. That ax plus b is now ex plus f.
Any way to like undo the square?
Undo the square.
Instead of completing the square, go backwards.
Could you write an example down of what you're thinking?
Right, well, right there. X squared plus 9. It's a square, but it's already a square.
So the difficulty here is that there's no x term in the middle.
Right.
So there isn't, like, well, the thing you add for the completing the square is b over 2 squared, right?
Yeah.
So you're adding nothing in this case. Well, we just can't do anything for this one. Just have a donut. It's fine. All right. So again, I'm not motivating anything here. I'm just saying, look, things can get more complicated. Just want you to have seen it. All right. You should write that down. I would never ask you to like actually find A, B, C, D, E, and F in this kind of a setup. I would never ask you to do that. But I might ask you to set it up. So I would like you to just practice a little bit with the setups, even if it's complicated. All right. So we're gonna jump down to number 7. And I'll say that, so we've just seen this new technique called partial fractions. A lot of people don't like partial fractions. Even fewer people like trig substitution, which is what we're about to do. So this is really as bad as it gets in terms of integration techniques. Here it is. So first, I want to tweak the problem a little bit. See that red dot? Cross off the 4 in this problem. Crossing it off makes it better. It's just not as hard. It's still a weird substitution. Value of red dot is 1. Thank you. Okay, here's what we're going to do. For reasons that will make no sense at this instant. I'm going to do this substitution. I'm going to let x equal 3 sine theta. You ever see like famous chess games that have been played out, and then you'll see like all the notation that says, you know, here's this move and there's that move, and then when there's a really good move, what do they put after it? Anybody know? It's not an asterisk. They put an exclamation point. Like if it's the move that's just like, all right, this is the one that's going to win the game, put an exclamation point. So I'm going to put right there.
Like a mic drop at it.
All right, so there's no reason to do what I just did, but let's follow this through and see what happens. So first of all, we're just going to start substituting. Okay, we're going to start substituting. Downstairs, I have a square root of 9 minus x squared. What are we putting now for some strange reason instead of x? 3 sine of theta, we'll just put it. There's a 1 up top. Put a 1 up there. What is in the original integral that isn't down here yet? The dx, right? That thing right there is not down here yet. So it feels like, well, I should just put d theta, but you can't. I mean, the dx is not the same as d theta. So we actually need to find dx, take a derivative of this thing. It's just what you do for u substitutions. Let u equal blah, and then right away, du equals, and you take a derivative. So what's the derivative of 3 sine theta? 3 cosine theta, d used to be, no, it's d theta. That's the variable. The thing. Okay, so instead of that circled dx, what are we putting here? Right. So granted, this looks worse than it did to start with. But does everybody at least believe that every piece of the original integral is now substituted for in the new integral? Yes. Okay. So let's proceed merrily along. Downstairs. So what are we doing here? This equals integral. All right, so downstairs, square root of 9 minus, when I take 3 sine of theta and I square it, what do I get? I like the sine squared. 9 sine squared theta. Everybody buy it? I'm going to put that 3 cosine theta upstairs. Yes, that's where we're headed. You do remember what it's called. Okay, what are we going to factor downstairs? And take that 9 outside. So still copying the 3 cosine theta d theta. Downstairs, it's a square root of 9 times, and then fill in the blank. Yeah, that's what we're putting now. So we'll pause to let people catch up, process. We just took this 9 out of both of these guys. All right, that's enough. That's enough. Okay, and then something really nice happens. 1 minus sine squared theta is a Pythagorean identity. What is 1 minus sine squared? It's cosine squared. I'll show you on the next page. It's written out. It's this. We all believe that sine squared plus cosine squared is 1. So just bring the cosine squared over. Bring the sine squared over, and we get 1 minus sine squared is cosine squared. So that's what we're putting here. So we're copying upstairs, integral 3 cosine theta d theta. Downstairs is the square root of 9 times what? Cosine squared theta. That's the idea. We're just going to take the plus. Exactly. So that part right there, it's still not clear that we're going to get to an integral we can do, but that moment right there where we got to replace 1 minus sine squared with cosine squared, that was why I did this very strange thing right here. I picked, why did I put a 3 there? Yeah, because there's a 9 sitting in the front, and what happened to that 3? It got squared and became a 9 so that I could then factor the 9 out of both parts. So I'll give you a formula on the next page, but that's why I did that very strange thing at the start. Like I said, it's not, well, I mean, it came out of someplace, and it came out of a desire to use that Pythagorean identity. Again, it's not clear that we'll have an integral we can do. But anyway, that's the moment right there that motivates why we're doing what we're doing. Equals. Okay, upstairs, we still have 3 cosine theta. What do we have downstairs? It is a plus or minus. We're going to ignore that technicality, just put the plus. Wait. Everybody see where the bottom 3 cosine theta came from? Square root of 9 cosine squared. So finally, we get to an integral that's very easy to do. Integral of d theta is theta. Okay, last thing. The original integral had x. We introduced theta. We can't have theta in our answer. So let's go back to the very first thing we wrote, which was x equals what? 3 sine of theta. We need to figure out what theta is so we can plug it back in. So x over 3 is sine theta, and then arc sine. Good. So that's our final answer there. So the reason we picked sine here is, yeah, if you ended up right here with 1 minus tan squared, that's not an identity. So that's why we picked a sine here. Any questions on the ending part of this? Mm-hmm. You guys remember this from the take-home quiz? This is equal to arc sine, yes? problem that we had, Chris is correct. It's really close to this. What did we have? What's the only difference we had? We had a 9 instead of a 1. So that's where the 3 comes from. The only difference between this easy one, which is it's on the take home, it's just a memorized thing, and the one that we had is the 1 became a 9. Well, it turns out the price that you pay for that is the square root of that number goes on the bottom. Now, the fact is you can add another thing to your formula sheet if you want to. It must be here somewhere. So I'm looking for, what am I looking for? It might be down at the bottom. Yes. Okay, what did we have again? We had square root of 9 minus x squared. How much was the a? It's 3. Yes. So according to this formula, what's the answer? Arc sine of x over 3. That's what we got. Well, the table is always easier. This is the back cover of your textbook. Yeah. All right, good catch, Chris. It's almost exactly the arc sine. Turns out this is how we pay for the 9 instead of having a 1 there. Good, good. Okay, on the next page, we have a couple of hints. So first, the Pythagorean identity that we ended up using there was sine squared plus cosine squared is 1. We're going to use a different one right now. Tan squared plus 1 is secant squared. Sounds familiar? Okay. If you see a squared minus x squared, for example, we had 9 minus x squared, yes? Then you let x equal a sine of theta. What was our a? A squared is supposed to be 9. Our a was 3. So what was our very first step? 3 sine of theta, right? Not so magical anymore. If instead you have a plus in between those things, then you let x equal a tangent of theta. Makes all the difference in the world. If it's a minus, it's sine. If it's plus, it's tangent. This is written on the first page of the packet, which you're going to bring with you to the quiz. You don't need to memorize, but that will be our guide. Okay, number 9. Cross off the integral in number 9. Replace it with this one I've written here in black. Yeah. So first of all, I could make this problem really easy. No, I'd have to change a couple of things. If I change this to a minus, don't change it. What else do I need to change? And then it'll be easy. Yeah. What is this integral? That's arcsecant. It's on the list. But I think we've already seen enough examples where changing an integral slightly makes all the difference between whether it's easy or impossible. This is somewhere in between, closer to impossible, but it's not quite there. It's on the spectrum somewhere. All right. Yeah. Okay. X equals. What do we have here? Right. So we have a squared plus x squared. We have a 1 plus x squared. How much is a? 1. So we're going to make the substitution x equals 1 tan theta. You don't need to write the 1. Okay, so we're going to start to substitute for this integral. Upstairs is a 1. Downstairs, instead of x squared in the front, tan squared, right? Square root of 1 plus and squared theta. Yeah, what's in the original that isn't here yet is the dx. It is tempting but wrong to just put d theta. You can't do it. Not only is it wrong, but there's a very good chance you're going to take an integral that was possible to do and turn it into one that's not possible to do. My guess is this one is not possible to do, but we're not going to put d theta there. We're going to actually calculate right here, dx. Secant squared theta d theta. Good. Yes, we can. Yes, but what we get might not be possible to do. I don't think that's what it would be. But you can write out what it, I don't know if it's possible to do it without the right thing over there, but you can try. Yeah, but you're not saying the right thing. This is not, you got to substitute that for something that we're about to do. But you're one step ahead of us right now, so let's come back. Instead of this dx, what are we going to put in our integral? Secant squared theta d theta. So I'm going to put it upstairs just because I've run out of room. Secant squared theta d theta. Equals integral. Upstairs, copy. Downstairs, copy until the radical. One plus tan squared theta. It's on the top of the page. It's an identity. It's secant squared. Everybody see it? Secant squared appears here twice for two completely different reasons. Why did this one on top here in blue? Why did this come in? Because that was the derivative of tangent, right? This one here in the bottom, where did this come from? That's the identity. It's 1 plus tan squared, right? Two completely different reasons that the same thing appeared. Okay, so we've got this new integral. Let's see if it's any better than the original. So equals, upstairs I'm copying. Downstairs, what do we get? Square root of secant squared is really secant. Yeah, so let's cancel one of those secants. Like, we've got this new integral, and again, there's no guarantee it's any better than the original, but at least it's different, something else to try. So we've got that, canceling one of the secants. Yeah, I think that's what we're going to do. We're going to change all of these things into sines and cosines and see what it really is. Okay, secant upstairs is really what other trig function downstairs? It's really a 1 over cosine, right? So that secant becomes a cosine down there. Tangent is really what over what? Sine over cosine. But this tangent's on the bottom. So it's really a cosine over sine. It's not arctan. It's the reciprocal. It's all squared. So I'll write this in purple. That tangent on the bottom is really cosine upstairs, sine downstairs, squared. Yes. All right, and Topher's right in that, you know, we've got everything with sines and cosines, and maybe we have more cancellation. And we do. What cancels? One of the cosines. So let's cancel one of the cosines. And we get, what do we get? Upstairs is cosine, downstairs is sine squared. And I'm still not saying that integral is easy. It's just different. We're just trading an integral, and we're hoping eventually we find one we can do. So how do we handle this one? I'm going to write it in one slightly different way, and then I'm hoping that some folks see how to handle this integral. So sine squared on the bottom is sine to the -2 upstairs.
Wait, so how did you do that?
Yeah, so different pieces went different places. So secant is really 1 over what trig function? Yes, so there's my 1 over cosine. I just put it in the bottom as a cosine. And then tangent is really what over what?
Oh, yeah.
Yeah, tangent is sine over cosine, but this is on the bottom. Right, so cosine over sine in purple, they're both squared. Topher. Yeah.
I did cosine over. Like I ended up getting
You can't simplify that because, no, it's not that it goes, you can't cross off the cosine like you just said. Mm-mm. If it were flipped over, you could cancel, but not the way it is. Okay, gang, we are done with this one once we see it. This is a U substitution. If we let U equal sine of theta, then du is cosine of theta, d theta, which is sitting in the front there. This is a trig sub followed by a U sub. We have U to the -2 du. Okay, what does this become? U to the -1 over -1. Yeah, it was absorbed in the du. Yes. So -u to the -1 is the same. And then instead of u, I'm putting sine. So this is negative. Yeah, so we'll write that as a -1 over sine theta. And then we're still not quite done. What do we need to do finally? We need to go back to x. Right, this is theta, which was one of our 2 different letters we introduced to solve this problem, but it's not the original letter. So we need to figure out what sine of theta is. So the very first thing that we wrote up here in blue is that x was tan theta. So you can solve for theta right now and just say, oh, it's arctan of x. So I'm going to write that down here, but I'm going to show you how I want you to do it, which isn't what we're about to do here. So first thing we wrote was this, x equals tangent of theta. So then solving this thing for theta, I'm going to get arctan of x is equal to theta, right? And so then over here, again, I mean, you can write it, but this is not what I'll be expecting as a final answer. Plus C. Instead of theta, what did we say? Arctan x. Yes. So did you buy this part? Yeah, so then instead of u, just replace u with sine of theta. But then we put it on the bottom. We did it in one step because it was to the -1. So that really just means 1 over. Yeah. Yeah, that's it. Yep. Okay, so this answer is correct. I mean, it's fine. It really is fine, but it's not how people generally write it. So if this was sine and this was arc sine, then they would just straight out cancel, right? Okay, they don't straight out cancel, but they do kind of work together in a way that we haven't made apparent by writing it as sine of arctan. Vince, did you have a thought? Oh yeah, you could write it as a negative cosecant. 1 over sine is. Here's how we handle, I don't know. Here's how we handle this. So here's what we're going to do. We're going to take a look at this thing right here. Tangent of theta is x, yes? I'm going to write that as a fraction. And then I'm going to ask you to remember your SOHCAHTOA. What is tangent? Opposite over adjacent, yes? So there's some angle inside of a right triangle where opposite over adjacent is supposed to be x over 1. So that's what we do over here. So we're going to draw a generic right triangle, and we're going to put a theta in there. And then you guys told me that tangent is opposite over adjacent. So that means that the opposite must be x, and the adjacent must be 1. So in that triangle, the opposite must be x. That's over here. Adjacent must be 1. That's down there. Let's find the third side by using what? Pythagorean theorem. Good. So we're skipping the details of getting that, but that's the Pythagorean theorem calculation there. And then I'm just going to ask you to look right here where the problem involved finding sine of theta. You have a right triangle. You know that sine is opposite over hypotenuse. You can read it from the triangle. Opposite over hypotenuse. What's the opposite? X over what's the hypotenuse? There you go. So that was, what was that? So that's looking at this thing here in red. We're trying to find the sine of theta. We know that sine is opposite over hypotenuse. We've got all the information we need here about theta because we filled in our right triangle. Opposite over hypotenuse. Opposite over hypotenuse. That's what sine is. So this is just an alternative. Instead of writing sine of arctan of x, we can write that, which is preferable in general. Which was our original, the sine of arctan? We finally got to an integral that we could do. We couldn't do any integrals. We did the integral, we're done.
Right, but it kind of looks similar to the original integral.
Yes. Yeah, it's not surprising to have that square root of 1 plus x squared pop up in the answer. Iris, I don't have anything for you to say, you know, why the 1 is better than sine of arctan. I'm just telling you that generally we don't write trig of arc trig right next to each other. We do this instead. Gopher. Again, we're looking at the lengths that people used to go to find antiderivatives. This is a nice problem in that all right, so it brings in the new technique, the trig substitution. It brings back all of the nice Pythagorean identities that we used to know and love. It also involved a U substitution in the midst of doing all of that. And then finally going back through these two. So I know we're just about out of time, but I'm so curious what Wolfram Alpha thinks about this one. I haven't tried. Well, let's try. Okay, so we're going to try here. Okay, so what was it? Integral of one plus x squared. What did we get? Did we get this? But you don't appreciate all that went into it, right? I mean, you know.
I do. I like somebody with that.
Yeah, it's pretty smart, isn't it? Yeah. All right. Yeah. That's okay. All right. So I think that is that. So have a wonderful weekend. Lots of practice with this. I know it is a hard technique. It's bringing together a lot of stuff. We'll do something completely different Monday if that makes you feel any better. 13.